I am Professor Antonio S. Marahas, and this is Digital Technique Fundamentals. Okay, so welcome back to our subject, Digital Technique Fundamentals. Last meeting, we discussed the different types or the two types of signal, that is the analog and digital signal. And then we also discussed the different types of number system, such as decimal number system, binary number system, octal and hexadecimal number system. Okay? Then we obtain the positional notation of each number system. And we notice that once positional notation is obtained from any number system, once positional notation is obtained, it becomes a decimal number. But dili pwede nga vice versa. In other words, dili pwede nimo ma-convert ang decimal into an octal directly. Or you can do that, but the method is very long. But you cannot convert immediately an octal number into binary or binary into octal using positional notation. So our discussion for today will be about conversion between bases. Okay, so that means that using this method, we will be able to convert any number system into another number system in a very fast way, no? Because there are two ways in converting a number system to another number system. One is using the long method, which is a series of division. But the other one is using the short method, which we will be discussing today. No? So we will be using the short method wherein decimal or binary number system is used as its base or reference number system. Okay? So what I mean is that once you convert a particular number system, let's say an octal number system, into hexadecimal number system, then you have to convert first the given number system into its binary equivalent before going to convert that into another number system. Okay? So example, you have 256 of base 10. We want this converted to base 2. Okay? So, again, as I've said earlier, all number system or given number system should be converted first into base 2 before converting to another number system. But in this case, you have a decimal number and we want it converted immediately into its binary equivalent. So, what we will do is we make a series of 1. Okay? Okay, then this is base 2. We know that these are binary numbers and 1 is the highest number in the binary form. Okay, now the 2 here, the first binary digit is actually equivalent to 1 in decimal number. Multiply it by 2, you have 2. 2 times 2, you have 4. 4 times 2, you have 8. 8 times 2, you have 16. 16 times 2 is 32. 32 times 2 is 64. 64 times 2 is 128. And then, next is 128 times 2 will be 200. I think 200. 128 times 2 16, carry 1, 4, 5, 256. Okay? Now, 256 here, if you notice that it is the given number. Alright? So, all you have to do is to use this number here. This becomes 1. And then, the rest is 0. Okay? Only this number here is 1, while the rest will be 0 in base 2. So, this will now be your binary equivalent in or using this short method. No? So, you have this is 0, 0, 0, 0, 0, 0, 0, 0, and this one here will be 1. Okay? The total, once you add 256, this is 1. Added to this value here, the answer is 256. Okay? So that's very simple. Now, another example. Let's say you have 3,253, okay, of base 10. Oh, this is very big, no? Let's say you have 531 of base 10. We want it converted to base 2 again. So again, you make a series of 1. Okay? This is base 2. So again, this is 1, 2, 4, 8, 16, 32, 64, times 2, 128, times 2, 256, times 2, 256 times 2, so you have what? 12, carry 1, 10, 11, carry 1, 4, 5, 512. Now, if you notice that 512 is still smaller than 531, so we will include 512 here. Okay? Then, we find a number here that once we add becomes 531. For example, this one here, 512, we should make this as 1 because it's still less than 531. Now, if we will add 256 to 512, then it is bigger than 531. So, we will make this 0. Right? Then, 128 added to 512, that is still bigger than 531, so we will make this again 0. 512 plus 64, that is still more than 531, so we will make this 0 again. Then 32 plus 512 is more than 531, so we make this 0. 512 plus 16, we will try this. So you have 258, which is less than 531. So we will make this 1. Okay? Because 512 is less than 531. And then if we will add 8, okay, so you have 16, carry 1, 3, 536, which is bigger than 531. So this should be 0. Okay, so that means that 8 will not be added. Then, we add 4. You have 12, carry 1, 3, 532, bigger than 531. So, we will make this 0. So, 4 will not be added. And then, you have 2. You have 10, carry 1. You have 3, 530 is less than 531. So we will make this as 1. And then when we add 1 here, the number becomes 531 of base 2. So this will now be your binary equivalent in the short method, using the short method conversion. Okay? So just make a series of 1 and then add or find the number here above once you add these numbers, it totals to 531. So whatever is not to be added, you make it as 0. And the one that is to be added will be represented by 1. Okay? So that's how we convert a decimal number into a binary number system. Okay? Now, let's say we have an octal number system. Or before that, let us say we will convert a binary number into the decimal equivalent. Okay? So let's try this one. You have 1, 0, 0, 0, 0, 1, 0, 0, 1, 1 of base 2. We want this converted to base 10 or decimal number. Okay? So all we have to do again is you represent this with 1 in decimal number times 2, you have 2, you have 4, 8, 16, 32, 64, 128, 256, 512. Okay? Then, you add a binary number with the decimal equivalent. Let's say, for example, this one, that is 1, so you have 512, plus this one, 16, plus this one, 2, plus 1. Okay? So 512 plus 16 plus 2 plus 1 is what? 512, 16, 2, and 1. So you have 10, 11, carry 1, 3, 531 of base 10. So that's how we convert a binary number into base 10 or decimal number system. Or we can also use positional notation. But it will take time in determining the value of this binary number into decimal number if we will use the positional notation, no? Whereas kani mas faster ang iyahang result. Okay? Masayon. Okay. Now, let's have another example. Let's say you have an octal number, say 3, 5, 6 of base 8. We want this converted to base, let's say base 16. Okay? From octal to hexadecimal number. So the first step again is to convert the given number, which is in this case 356 of an octal number, into the binary number system. Again, binary number system in this short method conversion is used as our reference number system. Okay, so 356 of base 8. How do we convert this to base 2? So the first step is convert 356 of base 8 to base 2. Okay, how do we do that? So we know that 8 to the 1, which is actually equal to 8, is equivalent to 2 to the 3 in binary form. This is octal, this is binary, no? Okay? So that means that one octal number is equivalent to, or 1 bit of octal number is equivalent to 3 bits in binary number. Okay? So again, this means that one octal number or one bit of octal number is equivalent to 3 bits in binary number. And we know that the biggest number in binary form is 1. So we make a series of 1, or I mean 3 ones, 1, 2, 3. That is 3 bits. And this one here again is equivalent to 1, 2, 4. Okay, binary 1 times 2 is 2, 2 times 2 is 4. Okay, then we find the octal or the binary equivalent of 3, 5, 6 in this manner. Say for example 6. Where is 6 here? That is what? 4 plus 2 is 6. So you make this 1, 1, 0, that is equivalent to 6. Alright? Then how about 5? So you have what? 4 plus 2 is 6, so you make this 0. 4 plus 1 is 5. So that is 5. And then how about 3? So your 3 will be what? You cannot use 4, so you make this 0. You use 2 and 1. 2 plus 1 is 3. So this is 0, 1, 1. That is equivalent to 3. So what will now be our octal number equivalent? Or I mean binary equivalent of this particular octal number. So 3, 5, 6 of base 8 is therefore equal to, what is 3? 0, 1, 1. What is 5? 1, 0, 1. And what is 6? 1, 1, 0 of base 2. That will now be the binary equivalent of this particular octal number. Now, we are not yet done, because our main purpose here, or main target here, is to convert this number system into base 16. Okay? Now, we already obtained the binary equivalent because, as we have said earlier, binary number here is used as our reference number system. Okay, then step 2. So, what is given now, or what is being derived, was a binary number. And we want this binary number to be converted to base 16. Okay? So, binary to base 16. Okay? So, when you say binary to base 16, 2 should be equal to 16. How do we do that? So, 1 bit of hexadecimal number system is equivalent to 4 bit in binary number. 2 to the 4 is equal to 16 to the 1. Okay? So, in other words, in every hexadecimal number, that is equivalent to 4 bit in binary number system. So, what we will do is, since we have already obtained the binary number, so we rewrite this one. We have 0, 1, 1, 1, 0, 1, 1, 1, 0. Okay? So is this correct? 0, 1, 1, 1, 0, 1, 1, 1, 0. Okay. So 0, 1, 1, 1, 0, 1, 1, 1, 0 of base 2. Okay? Now, again, as I've said, 1 bit of hexadecimal is equivalent to 4 bits in binary. So, we count the number of digits from right going to the left. 4 bit. 1, 2, 3, 4. You put a boundary. The boundary. Now, if in any case that this one here is only 1 digit, you can add additional 3 more zeros. But in this case, since this is 0, no need to do that. Dili na kinahanglan nga mag-add, because once you add 3 more zeros, 0 gyapon ang result. Okay? Then, this one here is again 1, 2, 4, 8. 1, 2, 4, 8. Dili, continue. Every time that you have boundary, you start again counting 1, 2, 4, 8. Just like in this case here. 1, 2, 4, 8. Boundary, again, 1, 2, 4, 8. Then you add these values here with a 1 equivalent in binary. So you have 8 plus 4 is 12 plus 2 is 14. And what is 14 in hexadecimal? What is 14? A is 10, B is 11, C is 12, D is 13, and E is 14. So this is E. Because there is no 14 in hexadecimal. So this is E, and then you have the same. You have E, then you have 0. So the final answer is E of base 16. So we can say that 3, 5, 6 of base 8 is equivalent to E of base 16. Okay? So we have already converted 356 into base 16, which is EE16. Again, how do we do that? The first step is to convert 356 of base 8 to base 2. Why? Because as I've said earlier, base 2 in short method of conversion is used as our reference number system. So, how did we arrive with this? You have 1 digit of octal is equivalent to 3 digit of binary number. So you make a series of 1, 1, 1, 1. Then you represent this with 1, 2, 4. And then you find, for example, 6. What is 6? That is 4 plus 2 is 6. So you have 1, 1, 0. 6. Then 5. 4 plus 1 is 5. 1, 0, 1 is 5. And then 3. 2 plus 1 is 3. So you have 1, 1. Then this one here is 0. And then just combine it together. So you will have 0, 1, 1 for 3. 1, 0, 1 for 5. And 1, 1, 0 for 6. Okay. Now, once the binary number is obtained, we can now obtain the base 16 or octal equivalent, hexadecimal equivalent of this binary number. And which is what? Again, for step 2, 16 or 1 bit of hexadecimal is equivalent to 4 bit in binary number system. So, since binary is already given, all we have to do is to count the number of digit from right going to the left. 4 digit. 1, 2, 3, 4. You put a boundary. 1, 2, 3, 4. And then boundary. If this is 1, then you can add additional 3 more zeros. Okay? Since 0 na siya, di rin na kinahanglan. Then, again, this one here is 1, 2, 4, 8. Stop. Because of the boundary. Again, start counting 1, 2, 4, 8. And then you add the numbers here with binary equivalent of 1. Let's say, for example, this one. 8 plus 4 plus 2 is 14. And that is E in hexadecimal number. Then you have 8 plus 4 plus 2 again is 14. And that is E again in hexadecimal number. So the final answer therefore is EE of base 16. So we can say that 356, which is our given number, is the equivalent to EE of base 16.